In this video, I hope to link the shape function of x with the shape function of the c. Alright, we know that there is a somewhat relationship between the x and the c, right? At first, you interpolate between the displacement and the x. And then after that, you use the x to interpolate between our x and the c in the c domain, or the length change to the lambda. Okay, so in this video we're gonna somewhat link them all together. Alright, since we have n1 is equals to this one, and we have another n1 is equals to this one, this means that this is equals to this one. Okay, so I'm gonna set up the equation. So I have x2 minus x. Alright, I have this thing over here, so simply take this. Alright, and then this is from here. Okay, now I'll just bring this 2 upwards to the side and multiply everything by 2. Now I have this thing over here, and then now this is 1 minus sigma. I'll bring this thing to the other side. Alright, and I'll bring my c, not sigma, sorry. I'll bring this c to the side, and I'll bring this thing to the other side. So if that's the case that happens, this thing will becomes minus. Alright, and my c over here from minus I'll become plus. Okay, so I'll have 1 minus 2, this thing over here. Alright, and then this thing I just expand 2 times x2 minus 2x. So what I have is this thing over here. So at the overall scale, this thing is being re-represented over here as I've written over here. Okay, and we know that 1 can be x2 minus x1 over x2 minus x1, because the denominator is this one. I can somewhat reform this one, because this everything is equals to 1 actually. So I can sub in this thing over here as this one. Alright, what I have is this thing over here. So if I were to take this x2 minus 2x2, I have minus x2, right? That's 2 minus 2x2. Minus x1 minus nothing. Minus x1 minus nothing is minus x1. Alright, and then minus 2x is plus 2x. Alright, the whole denominator is x2 minus x1. I have it over here. Okay, so my c is equals to this thing. Next stuff, I'm gonna bring this thing, I'm gonna bring it all the way up here. Okay, the bracket. Alright, and then I'm gonna expand this, and after that I'll have this thing over here, and this thing I didn't actually change, so I bring it all the way down here. Alright, it's just a quick derivations. The bracket over here. Alright, and then what we're gonna do next is to isolate the x. So what I do is to is to bring this to the side. So therefore I have plus and plus is equals to plus 2x. Okay, next, alright, maybe I should have a plus over here. Okay, next I'm gonna divide everything by 2, because I'm gonna bring this 2 down. So what I have is this is plus. Alright, maybe I should rewrite everything again. Okay, so I have this thing over here. Alright, I rewrite over here so you can see better. Okay, next I'm gonna bring this 2 divide, so I'm gonna divide everything by 2. Alright, so therefore what I have is something like this, divided by 2. Okay, and now I gotta differentiate. Alright, I'm gonna differentiate this is dc. Alright, this is in terms of c, right? I gotta differentiate in terms of dc over dx. Okay, before I do that, I'll have to let you know that I'll set this x as 0. Okay, why do I set this x as 0 is because, alright, is that I may be wrong, but is that if we can set any point of x over here, you still remember. Alright, you can set the x over here, you can set the x over here. For my case, I'll set my x at the middle of our bar. Alright, x. Okay, never mind. Let's continue first. Okay, I'll dc over dx this thing. Alright, I'll just leave the x over here by now. Alright, what do I have is that if I will differentiate c in terms of x, alright, then x2 will be destroyed, x1 will be destroyed because it's in terms of x. Right, so c x Ah, my fault. Alright, I shouldn't have done that just now. Damn it. Alright, I have dx over dc. Here I have dx over dc now. Okay, I will differentiate x in terms of dc. Since I have already in terms of x already, what am I doing just now? Okay, so I have dx over dc. If I were to differentiate in terms of c, this one will cancel, this one will cancel. So I have half c, I will have half x2, sorry, because c will be removed. I will have half x1 over here. Alright, is equals to dx dc. Okay, now if I were to factorize out my half, I will have half x2 minus x1, which is equals to dx over dc. And what is dx over dc now? Okay, this is equals to our Jacobian. And how does this Jacobian comes in is when you set your interpolation node, I mean your shape functions, as equals to the shape functions as this one. Maybe this is like half n, yeah. So this is just to let you know that they are interrelated to each other. Alright, and therefore this is our Jacobian. And just a sneak preview is that x2, macam sneak preview only, x2 minus x1 is your bar, your length of the bar. Alright, this is x2. Alright, as you can see, x2 is over here. This length over here is x1. x2 minus x1 is simply this length over here. Right, from here to here. And therefore you're talking about the length of this bar over here, which is L. So I can simply write x2 minus x1 as L. And what do I have? Because I have no space already, I have half L is equals to dx over dc. Alright, or L over 2 is equals to dx over dc. Or you can also rewrite this whole thing as Jacobian is equals to L over 2. Alright, and this 2, this number 2 over here is your lambda. If you still remember the lambda, where is it coming from? This is your lambda over here. I should cancel this actually. Alright, so your lambda is this. This is 2. Now L is this one. So you're taking L divided by your this piece over here. So it's something you're talking about. Half of this becomes this one. Am I right? I don't know. But anyway, this is something like the Jacobian. Alright, this is not something like a Jacobian, but this is the Jacobian. Alright, this is how the Jacobian works. You're taking each one of the shape functions and then set it equals to each other, and then you interpolate and then you rearrange again, and things like that. Right, differentiate in terms of their stuffs. And just the meaning of it is that the changes is that how dx change will affect how the dc change. As we just to also let you know is that all along what I've been doing, although we have show you this and this one, alright, we are simply mapping from u map to x, and from x we map to c. But this whole process of mapping, it does not change your system at all. It doesn't change your system at all. It's just simply changing the basis of how you look at things. Alright, but they are actually the same. They are all the same. Alright, so the Jacobian is one way to deal with the mapping and to link all the mapping all together as one family. Yeah, something like that. Okay, so in the next video we're gonna use this shape functions. I mean in terms of the Jacobian and other stuff that we have done earlier. Alright, I'm gonna include one more. We can include this as the Jacobian over here, over in this side. So we're gonna have all this. Maybe I should include the Jacobian over here lah. Anyway, you get what I mean. So we'll use the Jacobian to mix with the Galerkin's method, and eventually you'll get some finite element. Okay, but this is by far the case. Okay, so I should also remove this thing over here. This is also untrue. Okay, this is also untrue. So I'm just simply taking the geometry shape function to sub in into our Galerkin's method, and my Jacobian to sub in into and merge with the Galerkin's method to derive our finite element deriving K. Okay, so the geometry shape, the n, is being sub in into your Galerkin's method, which we have proved to you for the weak form. Alright, now we have derived Jacobian. We're gonna use the Jacobian and the Galerkin's method together to derive our EA over L. So we have fully utilized all what we have learned. and I shall see you in the next video.